they have a mind of their own, just to annoy me. Because now we have, so for those who came late, I'm sorry I had to go over the test before because of that technical failure. Okay, so we are with the expanding universe, right? But still people didn't believe it. Still people had doubt about it and didn't want to believe in a Big Bang universe. So there is this scientist with his team from University of Princeton. His name was George Gamow. You see his name here, George Gamow. They published a paper and they said, listen, if we live in a Big Bang universe, then just after the Big Bang, okay, the temperature started to cool down and all the photons, the light emitted during the Big Bang, will be able to escape finally, because they will not be absorbed by the electrons, right? So the Big Bang at the beginning, the universe was like a soup of electrons and protons. Light was bouncing around and could not escape. So just after the Big Bang, the light can escape, and look what's going to happen. So that's also for the pop quiz. You see here, I have a 1D universe. Can you all see? I have a 1D universe, right? That's my Pilates. They are cheap ones because they always break. But anyway, that's my 1D universe. And just after the Big Bang, everything started to cool down. So 380,000 years after the Big Bang. And what's happening to the light that escape? Can you see what's happening here? Expanding, stretched out. So the light that escaped from the Big Bang, first it was in UV, right? And because the universe expanded, now we have this light in the microwave. Okay, so that's what the paper predicted. It predicted if we live in a Big Bang universe, so all that little waves that escape should have been expanded, stretched out. Okay, so that's also in the pop quiz. If you look at the cosmic, at the electromagnetic wave, right? So say you start here in the UV, so high energy, and then you're gonna expand up to radio waves, right? So I don't know, last time electromagnetic, bless you, spectrum. So you see here, you start here in the UV, so all that is ugly. You don't want to be exposed to that. It can give cancer, it can, very bad, not good, not very nice. But if you start to expand the wave, you're going to go into the microwave and then radio wave. So he predicted that because of the expansion of the universe, we should be able to detect those microwaves. And this is called the cosmic, and you have a question on that for the test. This is called the cosmic microwave background. So it's the afterglow of the Big Bang. Okay. And that was discovered by those two engineers. And they were engineers, Arno Penzias and Robert Wilson. So they were working for Bell Laboratory, and they were not in astronomy, okay? They were trying to work again on the statics, right? That was like noise that you have everywhere for telecommunication. And they were just out of graduate school, and they used a huge antenna here, and it's like a scoop. They scooping. They were scooping all kind of radio waves, right, for the telecommunication. So they were more into that. They were engineers, and all of a sudden, it didn't matter where they look to. They were detecting those microwaves, right, predicted by George Gamow, except they didn't share the Nobel Prize with George Gamow. It happened several times, okay, because he's the one who predicted them. They are the one who observed them, and they were, of course, awarded the Nobel Prize in Sweden, and they didn't share it, which is very unfair. But anyway, let's move on. So microwave, I have a very short video to explain. just to make sure that you understand, I'm going to
If you look
speed it
up
up.
at the night sky in any direction, past
So this is a great channel, right? He has a lot of subscribers. It's called Minute Physics and super cool, very nice.
all the stars and more stars and galaxies and superclusters of galaxies, you will see light that has been traveling for 13.7 billion years to reach Earth. It's the oldest and most primeval light in the universe, a picture of our cosmos, and it's called the cosmic background radiation. Of course, you can't really see this light with your naked eyes because it's in the microwave band of the electromagnetic spectrum, but it is visible to radios and radio telescopes, and even makes up a small portion of the salt and pepper on an analog TV. Where does this luminescent background come from? Well, just after the Big Bang, the entire universe was still so small it would have been very dense, scorchingly hot, and because it hadn't yet had time to get rough and uneven, it would also have been scrumptiously smooth. For a while, things would have been so sweltering that electrons didn't settle down as parts of atoms or molecules, but instead roamed freely in a kind of red-hot cosmic soup. That soup would have had lots of light bouncing around it too, scattering off of electrons and protons like a hall of mirrors. However, as the universe expanded, there was less and less energy to be had in any one place. And when things had cooled to just below the temperature of the sun, pairs of electrons and protons no longer had the energy to resist each other, and they fell into the electromagnetic embrace we call the hydrogen age. These electrons were so enamored by their new proton love interests that they effectively began to ignore all the light bouncing around them. So with fewer free electrons for light to interact with, the universe suddenly became transparent, and all the pent-up light was sent forth in whatever direction it had been headed after its last scattering, doomed to travel alone and unnoticed through the cosmos. That is, until it bumps into something solid. When we finally see it here on Earth, this light has been stretched so much by the 13 billion year expansion of space that, like a record slowing down, its frequency and color have shifted from the original sunlight white all the way to cool microwaves. Thus, it's often called the cosmic microwave background radiation, or CMB. And just as we can tell the temperature of a red or white-hot iron from its glow, this light tells us the temperature of empty space, currently around 2.725 Kelvin, or minus 270 degrees Celsius. However, the universe isn't exactly 2.725 Kelvin in every direction. If we look closely, there are small and seemingly random but noticeable bumps all over the place, kind of like milk that's starting to curdle. Our best understanding is that these cosmic curds formed as quantum fluctuations in the otherwise creamy infant universe, and then began to coagulate as the universe cooled and expanded. It's hard to overstate just how small or unbumpy these fluctuations of temperature and density were to begin with. The hot or cold spots were only hotter or colder than their surroundings by a factor of about 1 in 100,000. That's like noticing that a bacteria makes a beach ball bigger. But while this clumping of the universe initially resulted in small variations like the ones we see in the CMB, later on the chunky curds of primordial soup attracted each other gravitationally, and they ultimately coagulated and coalesced to form all of the massive structures in the universe that we see today, like planets, stars, galaxies, and superclusters of galaxies. So when we look up at the night sky past those galaxies and see the ancient light of the cosmic microwave background radiation, we're literally seeing the starting point, the proverbial cream, if you will, from which the starry curds of the universe congealed. Or quite simply, proof that the moon really is made of cheese.
So it's a little bit fast, but I think you get the idea. So here there is another video about the discoveries made by Penzias and Wilson. But again, I don't know, I have my 1D um, universe that get tangled. But you see, after the Big Bang, you see this light escaped. So first it was in the UV, and then as the universe is expanding, you see this wave gets stretched out in the microwave. So we can look at this light just after the Big Bang. And what you see is a picture of the baby universe, right? We see something like this. So that was a probe, okay, launched in 2009, and its mission was to take a picture of the afterglow of the Big Bang, okay, the radiation emitted just after the Big Bang. So now it's microwave, but back then it was more into UV because it was high energy. And what you see is, first of all, the universe is homogeneous. This is because the Big Bang, happened exponentially, so faster than the speed of light. Remember that for the test? So they didn't have time, the universe didn't have time to differentiate through it. And what you see here, this is hotter, this is cooler, and these are the seeds for the future supercluster of galaxies, right? So that's amazing. And the first image that we get is from that big breakthrough that happened in 1965. And then we improved the picture that we have of the baby universe. right? So you're gonna have one or two questions about that.
Before astronomers could even begin to understand the life and death of stars, new telescopes would have to be built that could look at the
So I don't like him too much, but this is a very nice video. I don't know if I can go faster.
different wavelengths. Before that could happen, though, radio astronomy produced another great discovery that, although predicted, was as unexpected by its discoverers as Jansky had been. And once again, it happened at Bell Labs in Holmdel, New Jersey.
So remember Jansky? He's the engineer who launched radio astronomy, right? He detected the signal coming from the supermassive black hole of our Milky Way. He didn't know it was a black hole, right?
In 1964, Bell Labs had this spare 20-foot microwave antenna sitting dormant. Rather than destroy it, the lab decided to let astronomers use it for research.
No, first of all, they were
Two physicists, 31-year-old Arno Penzias and 28-year-old Robert Wilson, decided to use the antenna for measuring the temperature of the gas halo surrounding the Milky Way galaxy. What happened next is one of the most exciting discoveries in modern astronomy.
Hi, Bill.
Dr. Wilson. And I came to Bell Labs to get the story firsthand from Robert Wilson himself.
Two of us, Arno Penzias and I, had just come to Bell Labs from graduate school, and we were going to measure radiation from the Milky Way. And that's where this antenna really fit in, because we could reject the radiation from the Earth. And what was left is what's coming from the sky. We were only getting about 2 degrees from the Earth's atmosphere. Maybe pick up 1 degree from the walls of this thing. But when we first turned it on, it was about twice that. It was 7 degrees. And this just wasn't right. Something from the Earth must be in our instrumentation. We, of course, are on a hill here that overlooks New York City. We had the ideal instrument for checking on that, though. We merely turn it down to the horizon, scan the horizon, and lo and behold, nothing particular extra. There was a pair of pigeons that lived in here, and of course...
So that's the funny story, okay? For the next pop quiz, maybe, about the pigeon. I feel very bad for
was
them.
covered with white pigeon droppings. So we thought, well, maybe the pigeon droppings are doing more than we think.
So they are
Arno and I got up in here and we cleaned all the pigeon droppings out. Got rid of the pigeons.
What happened? How'd you get rid of the pigeons?
Well, first we put them in the company mail and sent them as far as we could, which was Whippany, New Jersey, to a pigeon fancier there who said, these are junk pigeons, and let them go. A couple of days later, they were back.
40 miles away, they came back.
Yes. So then our technician brought in a shotgun.
And then how did that work?
Well, I wasn't here, I didn't see it, but basically it didn't solve our problem. We still had an extra 3-4 degrees. We were really beginning to be perplexed because we believe in physics. It's coming from somewhere. We can calculate what the horn is doing except for this excess noise.
At the time that Penzias and Wilson detected the radio static, there were two competing theories about the origin of the universe. There was the Big Bang theory, which Hubble's expanding universe supported. And there was the steady state theory, which proposed that the universe is timeless, with no beginning or end, expanding forever. When a friend heard what Penzias and Wilson had found, he suggested they get in touch with some cosmologists at Princeton University who were advocates of the Big Bang theory. They believed that a Big Bang would have left a faint thermal afterglow in the universe, traces of heat from the roar of the bang itself, detectable across the entire sky. And they were about to conduct research in hopes of measuring that afterglow.
We invited them over. They came over and looked at what we had done and immediately agreed that we had measured what they were setting out to do.
So what does your discovery mean?
Well, it means that we live in a Big Bang universe, and that we're seeing the radiation from 300,000 years after the Big Bang. In many cases, when there's a paradigm shift in science, it takes a generation before people really accept it. But in this case, I think the world was ready for it. Human society is always worried about where they came from. There are religious stories in every civilization that's ever been found. And I think we have a definitive answer, that we came out of a Big Bang.
Before astronomers could even begin...
Remember the cosmic microwave background? It's really the afterglow of the Big Bang. And looking looking at this far, far, far away, we see 380,000 years after the Big Bang. But, sometimes in science you have a red tape, so it's forbidden for us to look really at the Big Bang. We can't. We cannot know anything in the universe unless you can collect light. So it's like there's a red tape. Can't. Up to here, you can. Beyond that, you can't. So it was a big breakthrough. And as I've said, he should have shared the Nobel Prize, but they didn't. So it led to a Nobel Prize for sure. Okay. Okay, so after that, also interesting here. So we were in 1965. Now in the 70s, as you all know, it was the Cold War, and you know how history likes to repeat itself. So that's why I like history, right? Right now, we were close also to the Cold War. So 1970s, it was the Cold War. So the Soviet Union and the US, they were spying on each other, and the US detected gamma rays burst. So burst of gamma rays, right? So first they were worried because they said, okay, Soviet Union is really into that new hydrogen bomb. Okay, we have to respond. And then they finally came to the understanding that those gamma ray bursts, so gamma ray is a very high energy wave, electromagnetic wave, right? So we're coming from space. Okay, so it was burst. So it was not coming from the Soviet Union. And you have two types of gamma ray bursts. You can have the short ones that happen when you have two neutron stars, for example, or a black hole and a neutron star orbiting each other, and they merge and they burn out energy. Or it can happen when you have a massive star. So that will be a long burp, at least 2 seconds. The short burp is less than 2 seconds. So the long burp can happen when you have a massive star collapsing before supernova. Okay, oof, they almost pushed the red button, but they understood it was coming from space. Okay, so exoplanets, that's also the thing that you have to remember. Arecibo, the Arecibo telescope, okay, detected the first exoplanets, right? And the first exoplanet, as I have told you many times, were orbiting a pulsar, a neutron star, an ugly star, which very surprising, because if there was a supernova, then there will not have been any planets, right? They will have been wiped out. So they think that maybe those planets, they needed a home and they were adopted by the pulsar or something like this, right? So after that, they found new exoplanets around a real star, a living star, because the neutron star is already dead. Okay, so that happened in the 1995, and that led to a Nobel Prize, right? So the first exoplanet orbiting a main sequence star, and that sequence star is Pegasi. So Pegasus is named after the horse of Hercules, right? I think the one that can fly. So anyway, so video exoplanet. So okay, I'm gonna save that for next time because I want to cover enough for the test. Okay, so here you have the next step. Okay, so the next step is 1990s, right? 1993, around there, they discover that not only universe is expanding, but it's spinning up. So remember Hubble's law? Okay, so as you see here, my universe is expanding, even though it's expanding at a constant speed. Okay, from my perspective, this one is moving faster than that one because you have more stretch, right? Even though it's expanding at a constant speed, from my perspective, if I live in that galaxy, the farther away, faster it goes relative to me. But now they had a new way to find distances, right? So they found a new way to find distances very, very, very far away just after the Big Bang. And they discovered that those galaxies, after the Big Bang, they were moving slower than the galaxies today. So that means that the universe is accelerating. And you had two teams for that, right? So you have the Supernova Cosmology Project, the High Z Supernova Search team. So you don't need to memorize those teams, but there were only 3 people getting the Nobel Prize because maximum is 3. So at least they share, not like the previous ones. And but they were very nice. So they invited everyone that was part of the 2 teams. They invited them in Sweden to attend the ceremony. So it's always nice to go to Sweden, and they got the Nobel Prize. Okay, so when you get a Nobel Prize, you have to share the money, right? There is money, so you understand why if 2 is more money than if you have 3. So anyway, they share. So that was very nice from them. So that was a big breakthrough. Okay, so they announced that in 1998, and that led to a Nobel Prize because Einstein, remember Einstein, um, before Edwin Hubble, people, scientists thought the universe is static, so not moving. So Einstein said the universe is static because there is a pull due to gravity, so pulling, trying to squeeze the universe, and then you have another force balancing out gravity. Okay, because if something is in equilibrium, that means that the net force is 0. If someone is pulling me in this direction and I want to stay in equilibrium, someone else has to pull me in the opposite direction, so I'm not moving. So he introduced a force which is called the lambda constant, the cosmological constant, lambda. So the universe was static. And then Edwin Hubble came and said, no, the universe is expanding. So Einstein said, this is my worst blunder of my life. Okay, that's my terrible mistake. I should not have introduced that force pulling on the universe to balance out gravity. Because if the universe is expanding from the Big Bang, it wants to keep moving at a constant speed because of inertia. So Einstein said, I'm stupid, this is my worst blunder. But now, 1998, Einstein has a big comeback. So that's why here you see him. He was very famous to smoke a pipe like Edwin Hubble. And I don't know, he's smoking multiple universes, right? Everyone knows that universe comes from the pipes of scientists or something like this. Because why is he coming back? Because they brought back his cosmological constant. Okay, so now you have to improve the equations that will explain the universe accelerating. So not only you have gravity squeezing, but now you have a dark energy, okay, making universe accelerating and even stronger than gravity. So they brought back his cosmological constants. Isn't that interesting? So it was 1998. It was all over in the news, right? So he came back from heaven or hell, and he was very happy. Okay, so this he's the author of your book, the one that I recommend if you are interested. The what is called the Cosmos in the New Millennium, and he was part of one of the team, right? So he, with his telescope here, which is called the Kate telescope, you don't have to know that, he was observing supernovae, right? And if you observe supernovae, you can find the distances to galaxies very far away. I can explain after the class if you're interested. But anyway, he's part of that team. If you want to understand dark energy, he has a very, very good public speech that you will find on YouTube, right? You type his name and you write down dark energy. So we'll explain the research if you want to learn more, right? Because I'm skimming through. So here we have the universe, right? We don't know most of it. Okay, almost 100%, 95% of it we don't know. We don't know what's dark energy, which is a force that makes things stretched out, right? Accelerating. We don't know what's dark energy. That's the glue that is gluing all the galaxies together inside those structures like Laniakea. And we only know that. Okay. So it's good. It's a red tape. That means you can get a Nobel Prize, right? If you find out what's dark matter or what's dark energy, there is opportunities for Nobel Prize if you want to change your majors. Okay, and finally, that was big breakthrough here in 2016. They discover, not discover, it was already predicted, right? Remember, they knew they had the proof for it, but they were not able to detect it. So they were able to detect it, gravitational waves. So in 2016, and you see, sometimes they wait for a long time to award the Nobel Prize, but here they didn't wait a long time. So I have a great video, just 1 year. It was so big in physics, the discovery of gravitational waves, that they didn't wait. They didn't wait. Okay, I think I have just the time.
What is a gravitational wave? It's a ripple in the fabric of space and time. Imagine that space is a giant sheet of rubber. Things that have mass cause that rubber sheet to bend, like a bowling ball on a trampoline. The more mass, the more that space gets bent and distorted by gravity. For example, the reason the Earth goes around the Sun is that the Sun is very massive, causing a big distortion of the space around it. Straight line around such a big distortion, you will find yourself actually moving in a circle. That's how orbits work. There's not an actual force pulling the planets around, just a bending of the space. Gravitational waves are produced whenever masses accelerate, changing the distortion of space. Everything with mass and or energy can make gravitational waves. If you and I started to dance around each other, we would also cause ripples in the fabric of space and time. But these would be extremely small, practically undetectable. Now, gravity is very weak in the scale of other forces in the universe, so you need something really massive moving very fast to make the big ripples that we can detect. How would you observe a ripple in space? If the space between you and me stretched or compressed, we wouldn't notice it if we had made marks on our metaphorical rubber sheet, for example, using equally spaced rocks, because these marks would also get stretched further apart. But there is one rule that doesn't get stretched, one made using the speed of light. If the space between 2 points gets stretched, then light will take longer to go from one point to the other. And if the space gets squeezed, light takes less time to cross the 2 points. This is where the LIGO experiment comes in. It has 4-kilometer-long tunnels and uses lasers to measure the changes in the distance between the ends of the tunnels. When a gravitational wave comes through, it stretches space in one direction and squeezes space in the other direction. By measuring the interference of the lasers as they bounce between the different points, physicists can measure very precisely whether the space in between has stretched or compressed. And the precision needed is incredible. To detect a gravitational wave, you need to be able to tell when something changes in length by a few parts in 10 to the 23. It's like being able to tell that a stick 1 sextillion meters has shrunk by 5 millimeters. The effect of a gravitational wave is so minuscule and easily confused with random noise, you need a smart data analysis technique. Scientists hope to identify the patterns of gravitational waves by comparing the wiggles they measure in the experiment to the wiggles they expect from the gravitational waves. That's like trying to identify a song being hummed at a noisy party, a very noisy party. Imagine your whole life you had been deaf until one day your hearing was restored. You'd be able to explore the universe in this whole new way. That's why detecting gravitational waves is so significant. It's a completely new way of studying the universe. Anytime there's a new way to investigate the universe, we discover things we didn't expect. It's really about looking for new things we didn't know existed, examining the extreme edges of our knowledge of physics, and testing our theories about how the universe works.
Okay, so it's that's also very nice. They make a comic book too. Let's see if I have a gravitational waves. I had like a, let's see if this one, I don't know if it's long. No, they explain how they do it. So because the speed of light has to be the same, if the universe is stretching out, it will take longer for light to arrive. If it's squeezed, it will be shorter, right? So when you have a gravitational wave coming to Earth, it's going to be shaking the space-time fabric. When it gets to Earth, the fabric will be squeezed and stretched, squeeze and stretch, squeeze and stretch, right? So using lasers, they were able to detect those gravitational waves, which means that Einstein was 100% right. Obviously, he was a genius. Okay, so if you are interested, you can look up here. And that was very new. 2017, you were already all around, right? So it's something very, very new. Okay, so for those who came late, I had to go over the test at the beginning. So you can ask your friends, you can buy them a coffee or something to share the information. Because I had technical issues, so that's why. Let's see if you have 6 minutes. 6 minutes about exoplanets.
They are nestled in the final frontier. Countless worlds, scattered throughout countless galaxies, challenge the notion that we are alone in the universe.
Giordano Bruno.
Exoplanets are worlds that exist outside of our solar system, also known as extrasolar planets.
So if you see Kepler, that means it's something that looks like our Earth.
Bodies often orbit their own stars, with some being a part of entire planetary systems. Exoplanets are made of the same elements as the worlds in our solar system, and based on their composition and structures are just as diverse. Some, known as giant or Neptune-like planets, are large gaseous worlds. Other gas giants, called hot Jupiters, closely orbit their stars, causing the planets to have high surface temperatures. Another category of exoplanets consists of super-Earths. Smaller than the gas giants, but larger than Earth, super-Earths are terrestrial and made primarily of rocky or icy material. The final category includes Earth analogs. Much as their name implies, Earth analogs are similar to Earth in various ways, including size, composition, and distance to their home star. Exoplanets are difficult to detect directly, mostly because they are outshined by the stars they orbit. To circumvent this, about 5 primary methods have been developed to find these planetary bodies, including radial velocity, in which a planet causes a star to wobble; direct imaging, where the glare of stars is blocked in order to see objects nearby; astrometry, which observes a star's movements in relation to nearby stars; gravitational microlensing, which observes the light of a star being bent by a planet's gravitational pull; and the most prolific form of finding exoplanets, transit, a method in which a planet passes between its star and Earth, thereby dimming its star's light. Scientists have suspected the existence of worlds outside of our solar system for thousands of years, but the first confirmed existence of an exoplanet orbiting a sun-like star only occurred in...
So 1995, that was planets around a star like our sun. But remember, for the test, the very, very first ones were planets around a pulsar, which was not expected, right, by Arecibo. And then came that discovery that led to a Nobel Prize. I don't know why the first discovery didn't lead to a Nobel Prize. I thought it should have, but I don't know.
1995. Ever since, about 4,000 exoplanets have been confirmed by multiple discovery methods, with about 3,000 more awaiting verification. According to one theory, at least one exoplanet orbits each star in the Milky Way. This would place the exoplanet count in our local galaxy to about 1 trillion. The search for exoplanets continues, not just to create a catalog of known worlds, but also to see if life may exist elsewhere in the universe. Astrobiologists closely study the size, composition, and location of exoplanets relative to their stars to see the likelihood of organisms thriving in an environment other than Earth. Who knows what discoveries these new worlds could bring?
Okay, and about gravitational lensing, let's see if I have something about that. It's also the proof for Einstein. So, for example, if you have a galaxy, the light emitted by the galaxy is going to be deflected by something very heavy, right? Maybe some dark matter or something like this, something or a black hole. So the light will go through the curve, and then we have a very weird image here. And this is called the Einstein ring. Okay, perfect. We made it. So again,